So good afternoon, everyone. Thank you for all of you to come to the seminar. So today we have our as fellow Professor Peng Zhang here. Professor Peng Zhang is associate professor from the City University of Hong Kong. Here for this role, he has had associate professor, assistant professor, then associate professor at Hong Kong Polytechnic University. Professor Peng Zhang got his PhD degree from Princeton University in 2010, and then continued as a combustion research fellow in the US. And then his expertise spans across droplet and spray dynamics, theoretical and numerical combustion, and chemical kinetics, and more recently, AI for science. And the floor is yours, Ken.
Okay, thank you very much. Thank you for your wonderful introduction and your hospitality. I had a very wonderful stay so far.
Thank you.
So it's my great pleasure and honor to be here as a visiting fellow of Institute of Advanced Studies. So today I'm going to talk about one of my favorite research topic, the droplet. So people are concerned about raindrop formation since a long time ago. In China, we have a myth talking about why the rains formed. So this Dragon King myth, right? When the Dragon King sleeps, then we have drizzles, and when the Dragon King speaks, that leads to a shower, something like that. So people try to explain why sometimes rain small, sometimes rain large. Okay. So later on, we know that the rain forms is because of the droplet. Okay, in the atmosphere, the two droplets might coalesce to become a bigger one, and the big droplets might break up into small ones. So in lithology, and it's very important, the research is to predict the raindrop formation and then the size distribution of the raindrops. So that's why many years ago, people started to use experiment to study droplet collision. So those are the early experiments. So you can see that depends on the impact velocity. And sometimes when two droplets collide, they might temporarily coalesce and then they separate. Sometimes this separation is associated with several satellite tiny droplets. Sometimes they just coalesce and then maintain the permanent coalescence, and after several oscillation of the coalescence, the droplet. And then I'm a combustion guy, so we're interested in combustion. So in combustion, we also deal with the spraying, right? So for example, this is non-Newtonian the engines. So we have the propellants inject into the engine, they collide with each other to help them to atomize into many droplets, and then they can facilitate the vaporization and the ignition and then the combustion downstream. And also we have some engines, they use the technique of impingement of jet and the sprays to enhance the atomization and the vaporization in a very limited space of the engine. So you can see that. Even you might argue with me that the droplet collision might not be that probable in a single spray, but once we have two sprays impinging with each other, then you have to admit that there are a lot of droplet collision going on there. So that's why people start looking into the droplet collision of liquid hydrocarbon droplets. So you can see that the most different phenomena compared with water droplet is that we found the droplet bouncing. That means when at a certain condition, when two droplets collide, they don't merge. Okay, after a while they bounce back. Actually, they never touch because we're talking about the droplet collision in atmosphere. So when two droplets approach each other, they will squeeze the gas between them to form a gas film. This squeezed gas film will have an increased pressure, which will prevent these two droplets from further approaching. So if eventually the droplet don't have enough momentum to squeeze the gas out, okay, under surface tension, they will bounce back. So that's the the physics behind this. Of course, we also have a coalescence and separation. So let me analyze the problem from the basic, the fundamental fluid mechanics technique. For example, we're interested in two droplets. They might be equal size or might not. This might be the same. Okay, so you can see that whatever we're interested in, that depends on the size, the impact velocity. Of course, this is a relative velocity. The impact parameter, how the trajectory of the droplet deviated from head-on, right? And also surface tension, of course, and then the density of the liquid and the gas, viscosity of the liquid and gas, so on. I put the dot here is because later on you will see that the controlling parameter for this phenomenon is way more than just macroscopic physical properties. We have some microscopic properties which also play a very important role in this problem. You will see that. So by using dimension analysis, which you guys all know, as long as you already take any fluid mechanics courses, we have several non-dimensional parameters. Wobble number, I need to describe it a little bit more because we're gonna use this number quite a lot. Wobble number is the ratio of inertial force to the surface tension force. Okay, so you can think large wobble number, that means there's a large momentum try to break up the droplet, and then the surface tension force try to hold the droplet as spherical, okay, without breaking up. And the impact parameter that shows whether we have head-on, we have off-center. And also number is to indicate how important the liquid viscosity is. Okay, so some people prefer using Rayleigh's number. It's just only a choice because Rayleigh's number is related to wobble number and also number through this relation. So basically, that's the same thing. You can say this is just viscosity effect. And the size ratio. Okay. Yes, there are two more. One is density ratio, one is viscosity ratio. Actually, in the early experiment, people, I assume they ignored, they didn't pay much attention to the influence of these two ratios. But if you think deeper, we are talking about droplet in engines, in internal combustion engine, rocket engine, which has a very high ambient pressures. And in that condition, the density ratio could be quite high, right? Because the density of the gas could be tens of 100 times of the normal gas density. So this ratio might not be decimal. Also, the viscosity ratio that depends on how viscous the droplet is. So after many years of study, we reach kind of a unified understanding of the regime nomogram. So showing here, the reason people show the result in this two-dimensional diagram is because wobble number and the impact parameter are the dominant parameters. Other parameters also influence the regime nomogram. They will shift the regime up and down and then left and right. You will see very soon. But basically, they maintain this kind of the picture. So you can see, with the increasing wobble number, we can have a coalescence. We call it a soft coalescence sometimes because this is a coalescence when droplets don't have much deformation. Then we have bouncing, coalescence, and then we have separation. Separation has two types of separation, depends on whether this is a head-on collision or this is an off-center collision. So you can, by the name, you can see reflexive separation. That means when it's a head-on, you have pretty much the symmetry, right? So it's reflexive. And the stretch separation is when you have off-center collision, you hit, and then the coalesced droplets start to rotate because under this condition, we have non-zero angular momentum. With very large wobble number, we even have a splashing case, which shows that huge impact to make the droplet break into many tiny droplets. So why do we care about droplet collision? It's because we want to do the modeling. Okay. On the one hand, we try to understand the science. We love the science. On the other hand, we want to do the modeling in the spray simulation. So this shows this is my favorite slide, showing that the holy grail problem in this century's combustion research is to develop the validated predictive multi-scale, multi-physics combustion model, which can help us to predict the combustion for variable fuel options and variable engine designs. We don't rely on the traditional way, try and error to design our engine. We rely on the computational simulation to help us to pick up several good choice, the design, and then we do the test. So if you look at this, you will see that for two-phase flow simulation, this is a really challenging problem. This is the year, and this is the size of the mesh. Okay, if you look at this is a work from the Japanese combustion researchers, Shinjo and Yamamoto, and anywhere. So you see, this is 3 cases, 400 million mesh, 1.16 billion. This is 6 billion. Okay, with the 6 billion mesh, they can resolve the mesh down to the 0.35 micron. Later on, you will see that even with this resolution, it's not enough to resolve droplet collision. That means droplet collision cannot be resolved in their simulation. You still need to do the modeling. Otherwise, you just introduce some artificial droplet coalescence or breakup. So that's why I always call droplet collision and breakup are numerical artifacts in their simulation. Even they call it DNS, but in my opinion, it's not DNS at all. Okay, they still have unsolved scales. So that's why we need the modeling. So we need to understand the scales of droplet collision and how they behave, whether we can find the rules controlling their behavior, and then integrate those models in our simulation. Simulation, I mean, could be a pure Lagrangian simulation. That means all the droplets are Lagrangian particles. We trace the particles, and then we study how particles interact with each other, and also interact with the gas phase. Okay. By simulation, I also means the hybrid simulation. That means the upstream could be a continuous simulation, for example, by using level set or using VOF, if you know what I'm talking about. And then downstream, we use Lagrangian particles. Of course, it's another challenging problem because we need some interface to deal with the transition from continuous VOF simulation to the discrete, the Lagrangian simulation. Okay, that's a different story. But both simulation, we need a droplet model. So my talk consists of 2 parts. The first part is a little bit simple, but contains all the necessary physics. Okay, and hopefully you can understand why I call this is a challenging problem, why this is a multi-scale, multi-physics problem. And then the second part of the talk, I will show you a lot more interesting phenomena by changing the influence factors in this problem. So head-on collision of identical droplets, you cannot find a simpler case than that. That means we have the equal size, the same fluid, head-on. Right away, we reduce our non-dimensional parameters into a field, right? So the particular phenomenon we're interested in is that we try to theoretically explain why with increasing Weber number, we can have coalescence, bouncing, and the coalescence again. Why can we have that? So let me very briefly explain to you the physics. As I said, whether 2 droplets can coalesce depends on whether the interface of the droplet can reach the van der Waals force. Okay, van der Waals force has the effective distance is about 10 nanometer, okay, 100 angstrom. So that means only you can push the two droplets into 10 nanometer or less, then the van der Waals force can take over and then make them to merge. So when these two droplets approach each other slowly, relatively slowly, so they don't have much deformation. They can comfortably slowly to squeeze the gas out between them, so they can reach the van der Waals region. If they approach each other faster, then they will squeeze the gas. The gas will build up pressure to stop them to further approaching, right? So this will prevent them to reach this distance, so they eventually bounce back. If we further increase the impact velocity, okay, anyway, since it's so much impact, we still can squeeze the gas out to make them to merge. So this is a qualitative interpretation of this phenomenon. And then the question is whether we can quantitatively explain that. Also, we have to understand why at 1 atm atmospheric pressure, water doesn't have bouncing. Okay, later on you will see that for water, if we increase the pressure, water can bounce back. Water droplet can bounce back. For hydrocarbon droplet, if we reduce the pressure, the bouncing can disappear. Okay, so we wish to establish the theoretical model to explain all these phenomena. So it turns out this is a quite challenging problem. So first of all, this is not the perturbation problem because the droplet undergoes the large deformation. Okay, this is not some perturbation that some partics can deal with. So the collision is inelastic. So we have a viscous dissipation through the internal motion of the droplet. But you can say this is much more complicated than the rigid body collision, okay, in classical mechanics. And also, as I said, this is something we recognize when we study this problem. Since two droplets coalesce only when they can reach the van der Waals force, 10 nanometer. But at 1 atm, the mean free path of the gas molecule is 70 nanometer. That means the mean free path is much longer, much larger than the van der Waals force distance. In other words, before the two droplets reach the van der Waals force regime, the gas flow between them is already rarefied flow. It's not a continuous flow anymore. This rarefied effect is not due to the reduced pressure, it's because the scales is so small. So before me, many people try to build a model to understand that. Eventually we found that unless you very rigorously, seriously deal with the rarefied gas effect, otherwise there's no way you can quantitatively predict the gas film drainage, the gas film dynamics. So you can see that the scales of the problem span about four orders of magnitude. So in terms of that, even direct numerical simulation to this problem is challenging. We tried, we haven't succeeded yet. Okay, later I can show you something. Okay, so we want to establish a model to include all these things together. And then eventually, to predict whether droplet can coalesce or bounce back, we look at the thickness of the gas film, and then we track the dynamics of the thickness changing with time. If they show something like this, that means eventually the van der Waals force take over a certain critical gap distance, and then rapidly drag these two interfaces to merge. Okay, that's the occurrence of coalescence. Otherwise, the surface tension will bring this H increase again. So that's bouncing case. So we establish a minimum model. The reason why I call it a minimum model is because we want to keep the physical components as few as possible, but grasp the in-sense physics here without additional unnecessary complexity. So basically, we'll have only three equations. As I always joke, in mechanical engineering, we always only need three equations: the continuity equation, momentum equation, and energy equation. That's three conservation laws, right? Whenever you try to build a model, think about three. So here we will have three equations, and then we have three unknowns. The first unknown is the radius of the spherical droplet, okay, with a flat surface. And then the radius of the flat surface is A, is also changing with time. It's the second unknown. The third unknown is the gap distance. So some people argue that in reality, this gas film is not completely flattened. The reason is simple, because the two droplets squeeze the gas is being squeezed out. So the pressure here is definitely higher than the pressure here. So since the pressure here and here are different, so then of course this high pressure will cause this droplet to deform inwardly, right? So to form this kind of a dimple shape. But on the other hand, you think this size, okay, is the same order of the droplet radius, and this could be the van der Waals force distance. So even though you look like a curve, but in reality, it's really, really flat with very, very small the curvature. Okay, but some people argue that this is not completely correct. I agree, because later I will show you some interesting things that it's because the curved the interface, we can have a trapped bubble in the coalesced droplet, because when the van der Waals force take over, they will make the rims merge first, and then you look at the axisymmetric, then you have the gas film trapped inside, and then form a tiny bubble. And this bubble is interesting. That will cause a micro explosion in combustion. You will see that. So, but for our purpose, we don't need to worry about this complication. So we have three unknowns, three governing equations, mass conservation, momentum conservation, and energy conservation, right? So to close this theory, we need additional information. For example, we need the flow inside the droplet, so we can estimate the viscous dissipation in the internal flow. We also need to find out what's the pressure within the gas film, okay? And then we close the ODE. So the droplet, the internal flow, this is an analogy of the famous von Karman's rotating disk flow. The difference is that now you can imagine this is big droplet. Okay, droplet squeeze each other, so the droplet deform. The deformed droplet is just like expanding the surface, the interface. The expanding the interface will reduce the flow to move like this. Okay, in von Karman's rotating disk flow, the disk, instead of expanding, is rotating. So they don't even see that. The reason we use this is because we can have a nice similarity solution, which means we can introduce the similarity transformation to convert the PDE problem into a nonlinear ODE problem. This is the boundary value problem. Of course, nowadays this is a simple ODE to solve numerically. You can do it very easily by using MATLAB, okay? But at that time, I prefer to push the analytical solution as much as possible. So I use the series solution. I do the perturbation series solution at the far near field and the far field, and match these two solutions together at a certain point to get a unified solution. So this is the final unified solution, which refer well with the numerical solution. Of course, it should be. And then to facilitate the calculation of viscous dissipation, I even found the approximate solution. Looks very simple, but agrees pretty well. So with that, I can estimate how much energy is dissipated within the droplet due to the internal motion of the deformed droplet. And then it turns out this flow is pretty much like a boundary layer kind of flow. So you can see this is later on we did a numerical simulation trying to justify this the velocity profile is really just like a boundary layer. Okay, that means only close to the surface of the droplet we have a large velocity gradient. Away from the interface, the velocity gradient almost zero. So that means when you calculate the viscous dissipation, you don't need to integrate the whole droplet, because at the beginning I just use a simple stagnation flow to estimate the viscous dissipation. It turns out it's overestimate the viscous dissipation. Then that's me. That's why I found this solution. Okay, the second closure term is the pressure within the gas field, because the radius is pretty large compared to the gap distance. So right away people saying, oh, this is a lubrication flow. Yes, it's pretty much like a lubrication flow. So this is the pressure gradient driven the viscous flow, right? There's no the initial terms. And then for hot sphere and the flattened sphere, you can calculate, you get the lubrication pressures. Here's one thing I want to point out is that hot sphere is easier to coalesce than the flattened sphere. If you look at this resistant force, the resistant force for hot sphere is inversely proportional to H, but for flattened sphere, it's inversely proportional to the H cube. That means at the same distance, H, the resistant force acting on the flattened spheres is much larger than that one. So that means if you use a fixed flattened sphere model, so you will always overestimate the resistant force, and then you will never get a coalescence case. That was the mistake I made when I started to do this kind of problem. Anyway, actually there's more, because we know that eventually the flow is verified. I try to use loosen layer correction, the slip boundary, the condition, this kind of first order approximation, I failed. Okay, eventually say, okay, I have to go back to the origin, directly solve Boltzmann equation. Okay, so this is Boltzmann equation I'm going to solve, and then assume the flow is quasi-steady and axiomatic. Use a BGK model. If you know a little bit about rarefied flow, you know that this is the simplest model to describe this collision integral. This collision integral, this is a integral. So basically, Boltzmann equation is a differential integral equation. This is the integral term. So this BGK model actually is a relaxation model, which means the distribution function of the gas molecules will relax to the local Maxwellian distribution with a certain time scale. Okay, that's the physical meaning. Okay. And then, of course, a long time ago, more than half a century ago, people already developed a whole bunch of technique to solve this problem. So I solved analytically, and I get a correction term, not fitting, it's just a series solution again. Luckily, it's because the lubrication-like flow, so the verified correction, it just add the additional multiplicative the correction term to the lubrication pressure. And this correction term is a number, is a function of a Nusselt number. Nusselt number is the ratio of mean free path to the characteristic length. So small Nusselt number, that means is close to continuous flow. Large Nusselt number, that means is near free molecular flow. And then when Nusselt number is larger than 0.1, we call it the rarefied flow or transition regime. So our correction term spans over the full spectrum of Nusselt number, all the way from continuous to free molecular flow. Okay, so we have this correction term. Eventually, we put everything together. Don't forget, we have one more thing, is the van der Waals force. van der Waals force, we use a simplified model, is just add the lactive pressure, attractive force on the interface. And this attractive force is inversely proportional to HQ. And then this harmonic constant is very small number. So you can imagine that normally, macroscopically, we will not see any van der Waals force because this constant too small. Only when H becomes extremely small, then this term becomes significant. Any macroscopic scale, you will not feel much van der Waals force at all. Okay, so put everything together. Now we're ready. The ODE model is closed. We can solve the dynamics of this three geometric quantity, of which is one mode because they're related, not totally dependent. So this is the coalescence case. So you can see the droplet is flattened. The radius of the flattened surface increases with time. Due to the mass conservation, because droplet is deformed, so the radius of the spherical droplet is slightly increased. H, the gap distance, rapidly decrease because at the beginning there's not much resistance force. Once they reach a certain point, the resistance force increases, so the H decreases much slowly until eventually they have the chance to make the van der Waals force take over, to rapidly drag this H to decrease rapidly. You can see this exponentially drop. So this is the coalescence case. Otherwise, you will get bouncing case. H decrease, struggling for a while. Eventually, they don't merge, they bounce back. So you can see the radius increase, decrease, recover to original spherical shape, and they all increase, decrease. So in terms of the theoretical prediction, so at 1 ATM, for water droplet, there's no bouncing. So our ODE model predict all coalescence case. For tetradecan 1 ATM, we have coalescence, bouncing, and coalescence. So we predict that, even quantitatively not that perfect, because considering this model is a minimum theory, right? We ignore so many things, and I think this is pretty much satisfactory. The coalescence and bouncing increase the wave number, keep increasing the wave number, get a coalescence scale. And also, as I promised, if we increase the pressure for water droplet, we can observe the bouncing. So this is the ambient pressure is 2.7 atm. We have bouncing case. Theoretically, we can predict that. For tetradecan, we reduce the pressure. Okay, no, we don't have bouncing anymore. So theoretically, we can predict that. So by that, our minimum model finish the job. They pretty much explain what we know at that time, about more than 10 years ago. So since maybe some of the audience are engine researchers, you're always interested in the question that how much your model can work in the really high pressure, right? The engine pressure. So for a long time, people didn't do the experiment under high ambient pressure. So in Zhang's work, they push the ambient pressure is about 12 atm, and that's all. That's about 30 years ago. Okay. So basically what they observed is that increase the pressure. Right away, you guys can predict. Bouncing will be promoted, right? Because increase the pressure, we have a denser gas. It's harder to squeeze the denser gas out. Of course, that will promote bouncing. Good, that's enough. For a long time, people think this is enough. Then the question is, if we keep on increasing the pressure to higher value, what's going to happen? Okay, so recently, actually really recently, last year, I and my collaborators in the Beijing Institute of Technology did an experiment. They have they have very good experimental facility and technique. They build up a high pressure chamber. They have a very nice remote control system. So we put everything, the droplet collision experiment facility within the high pressure chamber, and then adjust the droplet generator nozzle outside. Okay, because this kind of experiment is really challenging and really difficult. It really requires a great patience because it's really hard to get two droplets to collide in atmosphere. You are talking about the sub-millimeter droplet. You can barely see by your eyes, but you want to get them to collide head on, for example. So it's difficult. We get this experiment done. We push the pressure to gauge pressure 50 ATM, 50 gauge pressure. And then this is the numerical simulation. I guess some of the audience might familiar with this two-phase flow simulation, open source code, the Baslist and the Jervis. Okay, it's very nice, nice software developed by a French scientist. So the advantage of this software is the adaptive mesh. So this is off the tree adaptive mesh. Okay, so they really can resolve the interface. Okay. Now let me show you some results very quickly. So we don't need to start from one ATM, right? We start from gauge pressure 5, 20, or 5, 10, 20, 40, 50. Okay, these are the bouncing case. This is the experiment. This is our numerical simulation. They agree perfectly well. Yeah, it's very wonderful software. This is the word number 11, and then slightly off center. This is the coalescence case. Again, from 2 ATM gauge pressure to 50. This is the coalescence case. Okay. Now the interesting things is here. I'm a little bit excited to share with you. Is that normally we know that increase the pressure, the bouncing will promote. That means the critical wobble number between the bouncing and the coalescence will become larger, right? So then the question is whether this critical wobble number will be pushed higher and higher value if we keep increasing the pressure. The answer is no. This trend will level off in this way. That means increase the pressure. At the beginning, yes, we get a higher critical wobble number. That means you need a higher wobble number to make droplet coalesce. But once the pressure is high enough, this critical wobble number doesn't change much anymore. Okay, so we also established a model to explain that. I will skip this the difficult derivation. I just directly tell you the in-sense physics is that think about the rarefied flow. Okay, increase the pressure. That means the mean free path becomes smaller. Okay, 10 times 10 ATM. That means the mean free path is 10 times smaller. So at a higher pressure, the van der Waals force the rarefied flow effect is postponed to a later stage of the droplet collision. Even the later stage, as later as the van der Waals will take over. So that's why if you increase the pressure, you just postpone the action of rarefied flows to a later time, and eventually doesn't have much chance to play a role, and then the van der Waals force just take over to make droplet coalescence. So basic idea is just here. Okay, forget about the mathematical derivation. Hopefully you understand. Okay. How much time do I have?
10-15 minutes.
Okay, I try to finish in 15 minutes. Viscosity. There's another thing I didn't forget, viscosity. Previously, there's some debate about the role of viscosity. Because some people found when they increase the viscosity, Order number. Remember, order number is proportional to the liquid viscosity. Increase the viscosity, this boundary is pushed to the higher Waals number. That means increased viscosity, bouncing is promoted. Why? Think about what I said. Increased viscosity, droplet is harder to deform. So they can keep the spherical shape as much as possible. And the spherical shape can easily to squeeze the gas because the resistance force is smaller. Roughly, you can understand in that way. Right? But the other people found increase the order number. Bouncing is suppressed. Okay. But if you think deep, look at here. It seems like they are talking about different range of order number. This is a small order number range. This is pretty large order number range. So that inspired us to do a systematic experimental study by looking into the role of liquid viscosity. So we use a glycerol solution from 10% to 80%. We don't need to change. We lot these solutions with pretty much the similar density and surface tension, but they have very different viscosity. So the viscosity will change almost about 2 orders of magnitude. Okay, so you can see the order number. This is just around 0.01. This is 0.62. It's about 63 times difference. So with this wide range of order number, we believe we should be able to discover something. Yes, we did. We really found this trend that fix the Waals number, fix the impact parameter, only change order number. We can get order number keep increasing, right? We start from coalescence, we get a bounce, we get coalescence again. Right? As I said, at a small order number, bouncing is promoted. So we have bouncing case. But eventually the bouncing is suppressed, so we get the coalescence case again. And this is just not just this Waals number. Higher Waals number will have the same thing. You see coalescence, bouncing, and coalescence. The question is why? Why viscosity has such a different roles? So from here you can clearly see this trend, because basically this boundary, the black squares are bouncing, okay, and then the red triangle coalescence. So you can see with increasing order number, the regime of bouncing becomes larger, then becomes small. Okay, so bouncing is promoted first and then suppressed with increasing order number. Again, we need a paper to explain everything, right? But here I only have one slide to explain the physics. The key is the drainage time. Remember, whether we can have coalescence really depends on the comparison of the drainage time and then the droplet impact time. Droplet impact time is the size of droplet divided by the impact velocity. Right, this is pretty much fixed if we fix the Waals number. And then the drainage time is the drainage length divided by the drainage velocity. So we numerically study this problem. You can look at here. This is time, non-dimensional time. This is the radial coordinate. So you can see that with increasing the order number, the drainage velocity slightly decrease because the color shows the magnitude of a drainage velocity. It slightly decrease. But if you look at the drainage length, because the viscosity that prevents the droplet deformation, so you don't have that long passage to drain the gas out, right? So the drainage length also decrease with the order number, but much significantly. So if we consider these two things together, then we have that non-monotonic behavior. That's the key. Okay, so I think that's the simplest case, right? The rest of the thing is just some fun case. Let's do the collision of this similar droplet. Let's break the symmetry. The first symmetry we're going to break is the size symmetry. We have a different size of droplet. Then experimentally, what we observed is that let's don't look at the bouncing and coalescence. Let's look at the coalescence and separation. Increase the size ratio. Separation is suppressed. The reason is simple. The smaller droplet can squeeze inside the big droplet and then cause the larger viscous dissipation. That will stabilize the droplet. Very simple. That's the reason. Then theoretically, based on this physical picture, we can predict the trend. Okay. There's another interesting thing we found. We use the foot collar, the foot die, to inside a tiny droplet. Then we found this mushroom mixing. At the small wobble number, we have this like a mushroom, like a jet mixing pattern. Increasing the wobble number, this mixing pattern is gone. Increase the wobble number, this mixing pattern comes back. But it seems a little bit different from that one. Okay. At that time, we call this the single leg, one leg, this is the two legs. But what caused this? Well, one number is small, though, because the droplet don't deform that much. So when they merge at the central point here. Okay. So then the capillary pressure inside the small droplet is higher than the pressure this. So the pressure difference will drive the flow inside the small droplet into the big droplet and then concentrate along the axis because they merge at this point. Okay, so that's why they form a jet. Actually, we also use the vortex dynamics point of view to study this problem and get some scaling laws. Then skip that. And then one more thing is that if the droplet size difference is big, and then when this small droplet sorry move into the big droplet, and then at a certain time they will be pinched off to form a tiny droplet bounce back. Okay. And then we also predict the boundary of this pinch hole. For this case, the physical picture is totally different. In this case, we have a large droplet deformation. So the coalescence occurs at the rim, not at the center. Remember, the interface is curved, right? The rim has the smallest the gap distance. So the van der Waals force will make the rims merge first, okay? And then they form a crater, okay? And then this crater will move on like this, and then eventually you need to still have a remaining momentum to push this part of the droplet into the big one. So that's why if the work number is not high enough, we don't have enough momentum to make this part of the droplet get into the big one. So that's this case. And then otherwise we have this mushroom jet. And then this in two legs is the axisymmetric picture, right? I really run out of time. Okay, I skipped that. I also, as a spin-off problem, also studied how fast the droplet coalesce, try to understand how the surface tension drive these two droplets merge. They will form the liquid bridge. The radius of liquid bridge increase with time. So that shows how fast they can merge with each other. So previously people did experiment. They have scaling law at a different regime. We developed a unified theory to to explain whole thing. And then very recently this year, we finally got our paper published on JFM. We extend this study to unequal-sized droplet. It turns out the scaling law disappeared. We call it the breaking similarity, because we found this exponential the laws of the change of the bridge radius. But this one, under certain situation, can degenerate to that case. Okay, no problem. This is just one application of what I just mentioned, droplet mixing. Right? So you know that some of the combustion research know that mixing is the prerequisite of combustion. You want to burn something, you have to mix them up. So if you can take advantage of this mixing, then we can play around the things. So now we have two droplets. One is the tomato, tetramethyl ethylene diamine. This is the white fuming nitric acid. These two, you can treat this in the field, this oxidizer. They're hypergonic. That means you don't need the external ignition source. You can ignite them. Once they contact, right away they react through the liquid phase reaction. So, just okay. So, yeah. Okay. Let's go back. Let me explain. So this is the tomato. This is white fuming nitric acid. You can clearly see there's some vapor because nitric acid is very volatile. So there's some the wake shows the vapor. So they collide, they merge, okay, and then the mixing inside, and then to trigger the liquid phase reaction, and then the liquid phase reaction release heat to help them to vaporize. So the vaporize the fuel and oxidizer are mixed in gas phase and eventually ignite and react. So by the way, this is the propellant used in rocket engine for satellite orbital maneuvering. So the interesting thing is that we found the non-monotonic ignition delay with increasing wobble number. Normally we will think higher wobble number, that means we have a stronger impact. That we definitely will have enhanced mixing. Enhanced mixing, that will means the ignition delay will be shorter. Normally we will think about that like that. But in this case, you will see the ignition delay seems increase and then decrease. Maybe it's not clear here. It's here. Increase the wobble number, decrease. Increase a little bit and decrease. I still remember at that time my student came to my office with this result. He just simply draw a curve to fit this data. I said, hold on. I have the confidence to the uncertainty of our camera. We resolve the process down to the 0.2 millisecond. But look at this difference. It's larger than 2 milliseconds, 3 milliseconds. It's definitely not uncertainty. You repeat your experiment to confirm this phenomenon. He confirmed. So it's increase and decrease. So then we attribute this to this pattern. We have jet mixing, that's enhanced mixing. Then the mixing is not good enough, and then good enough again. But my another student, a colleague, later colleague, disagreed with me. He said, hold on, these are two different fields. They have very different surface tension. This surface tension is about 2 times smaller than the white fuming nitric acid. So the collision of these two will trigger some Marangoni effect. That means the small surface tension liquid will try to wrap up the large surface tension, the droplet. That will also influence the mixing. Okay, so he also did a numerical simulation to propose another thing. I really should skip that. It's a non-Newtonian effect. Okay, so we also can play with the mixing. It turns out, you see, this is 2 Newtonian. non-Newtonian, non-Newtonian, Newtonian, non-Newtonian, non-Newtonian, Newtonian. You can see that we only need the small droplet is non-Newtonian because it's the capillary pressure difference drive the small droplet into the big one. So if small droplet is non-Newtonian, this large strain rate will reduce the local viscosity. That will help the small droplet to concentrate the momentum, reduce the viscous dissipation. Microexplosion. We found that collision will promote microexplosion because microexplosion, by the way, that's all the known microexplosion. Okay, microexplosion is if we have two liquid fuel mixed together, okay, but they have very different boiling point temperature, okay, multi-component fuel droplet. So when they in a hotter environment, they're gonna vaporize. So what do you think? How they're gonna vaporize? You will think they will vaporize at the same time? No. So the low boiling point temperature fuel will vaporize first, right? The boiling point temperature is smaller. And then because vaporization is a surface phenomenon, so the high volatile fuel vaporized out, and then the high boiling point temperature fuel remains. And then at this time, droplet will keep on increase the temperature because we need to heat up the temperature to the boiling point, then they can vaporize. Then we reach the high boiling temperature, but remember that inside the droplet, we still have a low boiling point temperature fuel. They are overheating. Once they are overheated, if we have some nucleation, some bubbles, impurity, whatever, that will cause the nucleation and then the growth bubble. A bubble grows up, eventually they explode to tear the droplet apart into tiny droplet. This is a microexplosion. So microexplosion has two prerequisites. One, overheating. Two, you need to have a nucleation, right? So this bubble, trapped bubble by droplet collision provides, naturally provides a bubble there. They can promote the microexplosion. So you can see long time ago, they did an experiment. They used droplet collision to promote this. I think we have two more slides and then let you guys go. Droplet spinning. Remember, droplet can spin. For example, if you have two unspinning droplets undergoes off-center collision. Once they collide, they will rotate, and then droplet will start spinning. Also, when you generate the droplet, you use high pressure to push the droplet out of the nozzle. Also, this the shear flow, the ununiform shear flow will cause the droplet to spin. Okay, so we also need to consider how much the spinning motion of the droplet influence coalescence and bouncing, this kind of things. So we also did some work on that numerically, but experimentally that's pretty difficult. Recently we tried to let the droplet slide down from a slope to get some rotational velocity, but we haven't completely succeeded yet. Last slide. We can observe the coalescence, bouncing, and the coalescence not only for droplet and also for jet. Then you need to be very careful to generate a small velocity laminar smooth jet, and then you can reproduce this. Here, between them, we have a gas field, and this gas field will prevent them to coalesce, so they will bounce back. Okay, so in this case, locally, you can treat this as a two-dimensional droplet. It's not a spherical droplet; it's a cylindrical droplet, right? We also can have that. Okay, I think that's all I want to share with you, and hopefully you enjoy my talk. So to wrap up my talk, I want to emphasize that this is an interesting topic, It's multi-scale, multi-physics. We need to consider many physical influence factors to get things right. And then for future work, what I'm doing is try to realize the kind of like a simulation of a droplet collision to predict coalescence and bouncing. Okay, to add the van der Waals force and the rarefied gas dynamics into the WLF simulation framework to predict things computationally. Also, I'm doing this AI assisted model for spin simulation because there's so many parameters influencing the outcomes of droplet. So it's really difficult to use a single lice formula to fit all the results. You can see so many monotonic behavior, right? So why don't we use AI? Thank you very much.
Thank you.